Okay, so now let us start the second part of this lecture today. We solved that one. One more thing, I want to go through this a little bit fast here. So example number 9. Investigate the differentiability of the function f of x equals to the third root of x at 0. Okay, so let us see why I have mentioned this. So a function is given to us, f of x equals to the third root of x, and I have given you the point A to be 0, and I'm talking about the differentiability, investigating the differentiability of f at 0. So what we are supposed to do, let us write the formula. So f prime of A, in principle, if it exists, is equal to the limit of the function f of x minus f of A divided by x minus A, x goes to A. So this is the formula we just learned, the second version of the formula. And then I replace A with 0. Okay, so in principle, I shouldn't write f prime of 0 from the beginning because there is no guaranteed existence. So let me calculate this limit for this function, for this number. So this becomes the third root of x minus f of 0. F of 0 is 0. So let me write it, and then divide it by x minus 0. And x goes to 0. Yes? This is the formula. But what is your opinion? You should be very good now in calculating the limits. So if I want to calculate this limit, do you have any opinion? I didn't solve something like this in my lecture. I just want you to see, can you do this yourself? So what is your opinion about this? What then?
We can complete the cube, maybe?
Yes, something like that. Yeah. So how should I do that? I have to multiply it by 1 in a fancy way. But can you describe what the fancy way is in this case? So instead of writing 1, what should I write?
X to the 2 over 3.
Yes, the third root of x to this 2 power 2, but then I have to divide by the same thing, not to change the problem. But if you are a little bit doubtful why it works, just be patient a little bit. You see why it works, because the third root of x multiplied by the third root of x squared is the third root of x cubed. Yes? But what is the third root of x cubed? X. Do I need absolute value here? No, because 3 is odd. Yes? So this becomes just simply x. The denominator becomes x, the third root of x squared. And x goes to 0. Yes? But then, of course, this x and that x are cancelled. So this is the limit of 1 over the third root of x squared. So, is this limit indeterminate? It was indeterminate, but it is not indeterminate anymore. What type of limit is this? It is a number divided by a negligible number. If it happens, it is of which type? Infinity. Yes? But we also have to be careful, because sometimes it is plus, sometimes it is minus. But do you think it matters in which direction I approach to 0 here?
No.
Because of this even power here, it is always positive negligible. Yes? So it is always positive infinity. But what is your opinion? Is this function differentiable at equal to 0? No. Because do you remember I told you that if the answer to the limit is infinity, we still say the limit does not exist. Okay, so if you want to draw the picture of it, if you draw the graph of this function, the graph of this function turns out to be something similar to this. Okay, somehow this is the tangent line. Yes? But this tangent line is a vertical tangent line. And what is the slope of the vertical lines? We don't have it, but we can say, because the slope is the tangent, when I say a slope, if I have a line, if this angle theta, if I say a slope is tangent of theta. Okay? So if this becomes horizontal, theta is 0, tangent of 0 is 0. But if it becomes vertical, tangent theta becomes 90 degrees, and tangent of 90 degrees is not defined. Okay? So I just want you to know, is this function differentiable at this point? The answer is no. So can you more or less summarize the points at which the function is not differentiable? One category was the points the function is not continuous, but you haven't... no. One category which we learned a little bit was sharp points. Do you remember about absolute value? So, for example, this is also something like that. Might be I have a function goes like this and then goes like that. This function at this sharp point is also not differentiable. So remember, sharp points are indicating that the function is not differentiable. Another type of points we also learned today. Now, what is that?
Vertical.
If the tangent line exists but it is vertical, it's already an indication that the function is not differentiable. And the last category is at the points that the function is not continuous. Okay, so let me, for the time being, skip this problem number 10. It's a good problem. I think I will come back to it. Yes. Yeah, I'm in the stress of time. If I have time, I will come back to it. But let us start with this theorem. I have given it a mnemonic that you can remember. Differentiability implies continuity. And the content is very simple. If a function f is differentiable at a, then it is continuous at a. So let us at least see why this is true. So my point is that f is differentiable at a. My goal is to convince you that f is continuous at a. Yes? Okay. If I want to convince you that f is continuous, this is my scratch paper. If I want to convince myself that f is continuous, I need to check one thing. I need to take the limit of my function as x approaches to a and to see if it is equal to f of a. This is a scratch paper work. So I just see that how should I find a strategy to tackle the problem. This is what I want to do. Okay, but differentiability means what? Differentiability means that the limit of f of x minus f of a, x minus a, when x goes to a exists, and it is equal to f prime of a. This one is guaranteed because of my assumption. This one is the one that I want to achieve, yes? Okay, so that's why I'm saying this is the way you need to think. This is what you have, this is what you want. So you have to find a way to connect what you want to what you have. I mean, that is not easy, but you have to have a strategy. That is my strategy. I want to somehow algebraically do my algebra in a way that somehow I connect this fraction to this one so that I can see what happens. So immediately, hopefully, if you are a little bit experienced, hopefully you see that there is no difference between this question mark and this question mark. Can you complete the right-hand side for me?
0.
0. Again, the question mark. That is what I'm telling you. My goal is to show that this is true, but there is no real good connection between what I want and what I have. I have to be a little bit creative. So what I did to myself is that, okay, let me move this to the other side. First of all, do you understand that this one and that one are equivalent? Because this is a fixed number. If the limit of the first part is f of a, the limit of the difference will be f of a minus f of a is 0. So in principle, if I show this to you, hopefully you're happy because this will give me this. But do you see it's a good approach? Because at least can you see a little bit similarity between that now that I have with what I want? F of x minus f of a. Is that right? Okay. So what I will do, I will write it like this. So this is the proof. This is a scratch paper work. Okay? So I will say that the limit of f of x minus f of a, x goes to a. Tell me the algebra. The algebra is simple now. Try to be creative, yes? What do you think I will do now?
Multiply divided by.
Yes, because I want to have this at my disposal, yes? So I would write f of x minus f of a and then divide it by x minus a. So far this is illegal, yes? Because this is not equal to this one, unless I compensate for the change I made. What is the compensation? I multiply it by. Is that right? Okay, but now I have two things. I am going to calculate this limit. I convince you this limit is equal to this limit, but the limit of the first part exists. How do I know that? It is given to me. And what is the answer? This we know. Exists and is equal to this number. But the second limit, no one has told me anything, but this is so simple. What is this limit? This limit is 0. I can calculate it myself. Okay? So the limit of this function exists and is equal to this number. The limit of this function exists and is equal to 0. Then we had a theorem that the limit of the product is equal to the product of the limits. So this becomes equal to what?
0.
F prime of A multiplied by 0, but it becomes 0. Yes? So this is the way sometimes you need to think. Mathematics is hard, even for mathematicians, and that is the beauty of mathematics, you know. Yeah, mathematics should be hard, otherwise why? So let us say that you want to solve a Sudoku table, you know, every time you wake up and solve the same Sudoku table. What's the fun in it, yes? But the fun in it is that everything, you should think, be creative, and enjoy it, okay? Anyway, this is the proof. From now on, I want you to send it to your memory. F is differentiable at A, it guarantees you continuity, yes? Something which is very important for me for you to understand is that this is called a conditional statement. If P, then Q. This is the way we read it. Every conditional statement is equivalent. Let me use it like this. Every conditional statement is equivalent to its contrapositive conditional. Contrapositive conditional means not Q, then not P. Okay. So, for example, if you get A in this course, I will buy you an ice cream. So it means that if I don't buy you an ice cream and I stand on my word, it means that you didn't get an A.
Yeah.
So these are equivalent things, mathematically. So this, if I give it a name P,
No, it makes sense.
this is P. This is a statement. It is declaring something. F is differentiable at A. I call it P. Then I call this Q. So if P, then Q. As what I told you, this statement is equivalent to its contrapositive. What does it mean? It means you replace the statements, but negate them. Now, can you read the negation for me? So it means that instead of writing P, then Q, I write not P. Can you tell me what is not P? F is not continuous. F is not continuous. Yes, then not P. What is not P?
Not.
F is not differentiable. Yes, F is not differentiable. So this is not a new theorem. This is the same theorem expressed in a different language. Whenever you prove a conditional is true, a conditional statement is true, automatically you have also proven that its contrapositive is also true. These are not two different proofs. One mistake is that people take the other way around sometimes for granted. There is no guarantee. If I show that P then Q is true, Q then P can be true or false. Yes? I will come to you. Okay? So for example, if I say that if x to power 2, if x to power 3 is 8, what can I conclude? I can conclude that x is 2. This means that if x is not 2, then x to power 3 is not 8, which is also true. If this one is true, the contrapositive one is guaranteed to be true. Okay? But don't push this more. Okay? For example, if I say that if x is 2, then x to power 2 is 4. Is it true or false?
That's true.
That is true. But let us replace them and write x to power 2 is 4. Then you conclude x is 2. This is false because there might be 2 or negative 2. So this is true. This is false. This is true. This is false. This is also true. Sorry. So the contrapositive is always the same value. It has the same logical values. So for example, what is the contrapositive of this one? x squared is not 4, then x is not 2. That is also true. Yes? So whenever you prove a statement, a conditional statement, automatically you also have proven the contrapositive statement. But don't take it for granted. If P then Q does not guarantee Q not then P, it can also not falsify it. It depends on the situation of the problem. Is that clear? So now if I go to this remark, remember, f is differentiable, it guarantees continuity here on the slide. If f is not continuous, then f is not differentiable. But if f is continuous at a, there is no guarantee that the function is differentiable at a. What was the counterexample? What was it? For example here, this is continuous, but it is not differentiable. This is continuous, but it is not differentiable. So this is a very simple, very important theorem to know. Okay, sometimes this is the type of question that you might receive. I will solve one of them and then you can work on it, work on the other one yourself. So consider this function. Determine a and b so that f is differentiable at 2. Okay. So I want to tell you something. So how many unknowns you see in this problem? So, no, unknowns. X is a what is it called? It's a variable. By unknowns that I want to find. What are two? One of them is A, one of them is B. So differentiability is how many constraints? How many constraints give differentiability is? How many pieces of information differentiability provide for me? When I say a function is differentiable, it means that the left derivative is equal to the right derivative, yes? So how many pieces of information one equality gives you?
Like 3. That's the function at that point is the same.
No, what I'm saying is that when I say differentiable, it means f from the prime from the left is equal to f prime from the right. Yes?
Okay.
So let me write it alpha so that you don't confuse it with the a in the problem. So when I say that my function is differentiable at point alpha, this gives me this. This is how many pieces of information? How many pieces of information is this?
This is 1.
One piece of information. Yes? But how many unknowns are there in the problem? A and B.
Yeah.
So this means that you need to find another piece of information which is somehow buried in the problem. So differentiability on its own will not be enough. It is not wrong. It is one very big part of the problem. But you already know that it gives you one piece of information, but you have two unknowns, so you need another piece of information.
You can find a relation between A and B.
Yes, what I'm saying is that what is the other piece of information we just learned? It has to be continuous as well, even if the problem is not mentioning that. Because you would say that if the function is not continuous, it is automatically not differentiable. Because I want the function to be differentiable, it should be, of course, differentiable in this sense. And because of the theorem we learned, we know that it should be also continuous. So then continuity, one piece of information, differentiability, another piece of information. So I have two pieces of information. How many unknowns I have? 2. So it matches. Okay, so this is the way, that's a very good way to understand what to do. Okay, and then you know that you want to find continuity. Continuity is always easier to check, and I really want you to check the continuity first. So x squared, but this you have to write it in the exam. Yes, you need to say that because this function is going to be differentiable, so it should also be continuous. Write some sentence about it, okay? So x is less than or equal to 2, and then what do I have? I have ax plus b, x is greater than 2. So this is not wanted, this is what I learned myself. So continuity. Okay, so what should I write? I have to write the limit of f of x, x goes to 2 from the left should be equal to the limit of f of x, x goes to 2 from the right. It should be equal to f of 2, yes? Okay, so let us calculate this one. If you don't mind, let me call it A. Let me call this one B. So a is equal to limit of the function when x goes to 2 from the left. It means I have to choose this one. X goes to 2 from the left. The answer is 4. Yes? And then what is b? b is the limit of f of x, x goes to 2 from the right. So I have to choose this one. X goes to 2 from the right. What's the answer?
2a plus b.
b. And if you want, of course, what is f of 2? 4 again. Yes? So these three numbers should match. Two of them automatically match. So it means that 2a plus b should be
4.
This is one piece of information. Yes? Now I have to use differentiability. So 2 differentiability. Okay, so what should I write? I have to calculate the limit of f of x. Yeah, the formula is up there, okay? So if you want to refresh your memory. So f of x, I want to send it to 2 plus. So I have to choose this one for f of x. Can you see that? F of x is ax plus b minus f of 2. F of 2 is 4 divided by x minus 2. Are you okay with this? So what I have done, do you have these pointers? No, I don't know where the pointers are. Yeah, here. I am replacing a with 2, and f of 2 is 4. Yes, x minus 2, 4, and instead of f of x, because I am considering the right limit, I am putting it ax plus b. Yes? Is that okay? But now, how can I calculate this limit? Because if I put 2 here, what happens? The denominator is 0, but when I put 2 here, what happens? It becomes 2a plus b minus 4. But 2a plus b is equal to 4 already, so it is as always 0 over 0. But let us use it in some way. How can I use it? Because I want to continue and calculate the limit. For example, here I understand I need b. I go back and find b from this equation and take it with me and put it here. So this becomes, you see, I couldn't anticipate that I have to do this. So you have to be flexible. You reach to this point and then you go back, you need this, you put it here. So this becomes ax plus 4 minus 2a, and then I have minus 4 divided by x minus 2, and it becomes very simple now. Yes, because this 4 and that 4 are gone. Between this one and that one, a is in common. I can factor it out. X minus 2 divided by x minus 2, x goes to 2 from the right. But this x minus 2 and x minus 2 are gone, so what's the answer? Is a. Okay, so this means that the right side, the right derivative exists, and it is equal to a. And then what is the next step? The next step is to calculate f prime of minus 2. Again, you shouldn't write it immediately. Okay, so let us calculate limit of f of x, the same formula, but x goes to 2 from the left-hand side. Okay, can you help me now? What should I put in the denominator? Yeah, say something. X minus 2. X goes to 2 from the left. So what should I put in the numerator? F of x. Which f of x I have to put there?
X squared.
X squared, because x is less than 2. And then minus f of 2. F of 2 is again 4. Yes, but this is an extremely easy one. So this becomes x minus 2, x plus 2, conjugate rule. X goes to 2 from the left, this one I cancel, so the answer is 4. So what does it mean? It means the left-hand side derivative exists and is equal to 4. So then differentiability demands that these two numbers should be the same. So it means that a should be 4, and if a is 4, you put it back here, you get b is minus 4. Yes? So it's a very, very standard problem. The next one is a little bit harder. But now by the experience you got, I hope that you can solve that problem yourself. Any questions? Okay. These are only the problems, so there is no new lesson in these problems, as you see. They are good questions, but I also chose some exam questions. These are more theoretical questions. These are hard ones. I want you to think about them, and then you can have it in your seminar day and then discuss it with your TA. And of course, we can also discuss together. My goal is to write and solve these as videos and publish them. But I cannot promise how fast I can go forward. Okay. Any questions so far? Any questions? Okay. Now, what happens is that you see that if I want to calculate the derivative, even though the functions I introduce are among the simplest possible functions, but they are still messy and a little bit lengthy to calculate. Okay? And by the way, the functions that are involved are the simplest possible functions. If I have a little bit complicated function, which usually happens in, for example, engineering or physics problems, in real life problems. So using this definition of the limit all the time to calculate the derivative is not very efficient. Okay? So, and then the problem is that these are so sensitive. For example, when I calculate this at point 2, then when I change 2 to 3, unfortunately I have to redo the problem all over again. There is nothing simple that I can fix. I say that, okay, this is for 2, for 3 is this one immediately. No, I have to redo all the calculations again from scratch. And then, of course, it is not very efficient. So, if you are a mathematician, how do you think to solve this problem?
Generalize and then remember that.
Yeah, you need to find rules for particular functions, yes, for functions, and then remember them or tabulate them, use them. Okay? But there is one problem here. The problem is that how many functions are involved in the whole universe? There are infinitely many. So so the ideal scenario is that I have one single formula for every function, which is not, I mean, in principle it might be possible, but practically it is just useless. So what is the another step, even though the idea is this, but it is not practical, so we have to find a little bit better practical way. If you are a mathematician, what do?
Formulas.
You categorize your functions. For example, say that I have polynomial functions. If I find a formula for polynomial functions, any infinitely many polynomial functions are done. Yes? And then I have trigonometric functions. I have logarithmic functions, and that's the problem. Even though there are infinitely many functions, but still there are a lot of categories, but not at infinite. So it is manageable. So that is the rest of this is the motivation behind the rest of the problem. So it means that we want to learn about differentiation rules. Okay? So we want to learn some rules to differentiate faster, not every time go from scratch and calculate using the limit process. Is that right?
Yes.
Okay, so that's the idea. Okay, and there will be two different type of formulas. So in principle, I want to do this. So I will have general formulas. By general formulas, I mean formulas that are valid for all possible functions. It doesn't depend on the type of the function you are involving. And then we have particular functions. Okay? So in the particular functions, you have to have a good memory. These are not that many, so you can, most of them are natural. So you can remember them, you have already learned them in high school. But this one, we add some formulas. So it is a function and its derivative. So what is the simplest possible function?
0.
0 is a particular case of a broader perspective, a constant function. Yes? So if I have a constant function, its derivative becomes
0.
0. Okay? So if I have a constant function. And the proof is not hard. I will give you some idea about the proof. So because, for example, what do? You say that limit of f of x plus h minus f of x divided by h goes to 0. Let us say that my function f of x is constant. So what is f of x? Is the constant c. What is f of x plus h? Because this is a constant, it doesn't care what you say. It's like a dictator, you know? Whatever you say, it says C. Okay? So f of x plus h is also C. And then c minus c is 0, so this limit is 0. Okay, so that's why the derivative of a constant is 0. Yes?
Why is it indeterminate?
No, it is not indeterminate. That's a good question. Is it indeterminate or not?
No.
No, because the denominator is infinitesimal, but c is a fixed number minus itself is not infinitesimal, it's exactly 0. So it is 0 over infinitesimal, which is not indeterminate. That's a good question. So this limit is 0, yes? So if that is a constant, that is 0. Okay. But, so for example, if I tell you the function f of x is equal to, I don't know, sine of 50 degrees divided by logarithm of 75 minus 2. So what is the derivative of this function? What's the derivative? 0. Because that's constant. If you have a calculator, you put these numbers in, you get a fixed number. And that is the meaning of a function to be constant. So we don't care how it is written. If it is a fixed number at the end, the derivative is 0. Yes? So any constant function. So the first formula is very simple, I put it here. But there is some rules here, let me also put some rule here. The rule is that if you give me two functions, f and g, and you tell me that these two functions are differentiable, then the theorem tells you that the sum is also differentiable and it is equal to the derivative of the first one plus the derivative of the second one. Okay? So these are general formulas. You see, I don't tell you what g or f are. They are just two functions. What I tell you, they are differentiable. From this, you can guarantee that the sum is differentiable and the derivative of the sum is equal to the sum of the derivatives. Yes? And then if this is minus, that will be also minus. One more thing is that if you have a constant multiplied by a function, c is constant, and if you take the derivative of this one, you don't need to do anything with c, you just copy and paste c. You differentiate your function and then you multiply. Be careful, that is a constant. Okay, for example, let me at least give you some motivation about why this formula is correct for the plus one. Because I see in the workshop problems you have the harder one. The harder one is the product one. Okay, but let us give you some motivation here. So why this formula works? So let me tell you the sum. Let me consider the sum to be this. So I want to work with S as the sum, and my question is that what is S prime? This is my question. Okay, where is my starting point? Can you guess? The limit, because I want to prove any formula. So S prime of x is equal to the limit, let me use the first formula. S of x plus h minus S of x divided by h goes to 0. Do you agree?
Yeah.
Okay, but what is the meaning of S of x? H goes to 0. S of x is f of x plus g of x. There is a minus sign behind that. But can you tell me what is S of x plus h?
F of x plus h.
Yes, f of x plus h plus g of x plus h. Do you agree?
Yeah.
Okay, but now, I hope that you understand, this is simple. That is why product rule is harder to prove. This is very natural. I multiply this minus sign in. I will take minus f of x and write it next to it. And I would write minus g of x next to it. Yes? So let me write, and if you have any questions, let me know. If I write this, are you okay with what I'm writing now? Are you happy with what I'm writing?
Yeah.
I did some algebra, I didn't do something deep. I moved minus f of x here, I moved minus g of x here, but I splitted them and wrote it in this way. Why is that? Because if I take the common denominator, h will be to the denominator and they will be added, which I will get the same thing. So I did nothing wrong. But is this correct? The limit of the first one exists? Yes, because you told me f is differentiable. So what is the first limit?
F of
F prime of x.
then.
What is the second limit?
G
G prime of x. So this becomes f prime of x plus g prime of x. Is that right? So the hard one is for the product one. Okay, so try to work it out. And of course it is in the book that you can see the proof. But I think you understand a little bit. So whenever you want to prove a new formula, there is only one way. Go back to the definition, limit definition. Okay, so there is no other way. Okay, so now the next one here, I hope that you can see that these three formulas together can be written in one single formula, yes? So what does it mean if I want to write, for example, if I say 2f plus 3g minus, I don't know, 4k, these are functions and I want to differentiate them. So what can I write? I can write 2f prime plus 3g prime minus 4k prime. Can you tell me in going from here to here, which one of these formulas are used? I want you to feel it. So this is the way you do it, and you just do it like this automatically and quickly. But which formulas are being used in order to go from here to here?
Both.
Yeah, both of them. So this formula and that formula. Because the reason that I can just pull a constant out is just coming from the next one. So this one is also easy to prove using this. Okay? Any questions? Okay, so these are general formulas. Let us go back here. So let me see. Let me keep the order of the lecture notes so that you are also not confused. So let me also show you. For example, I told you that if a function is constant, its derivative is 0 for every x. For example, if I give you a square root of 2 and I ask you what's the derivative is 0. If I give you this function, its derivative is 0 because it's constant. So one of the very important formulas, hopefully you remember it from your high school, is that I have a power function. X to power r, its derivative is this one. There is no time to prove it. You can see the proof in the book or in the exercise session. But do you remember the formula from your high school studies? Yeah, so let me make it a little bit bigger. So, yeah. So if I have x to power r, if I want to differentiate, r goes to the back, and then 1 unit is subtracted from the power. Okay? Of course, whenever this is defined. Okay. So let me clean the board. So can you, as I am cleaning the board, can you tell me what do I mean by a power function?
X squared.
No, power x squared is one particular case of a power function. But can you give me another example of a power function?
X to the 2/3.
X to the 2/3, yes? So, what is the difference between a power function and an exponential function?
The variable in the exponential function is in the exponent itself.
Very good, very good. So that's extremely important because we haven't talked about exponential functions yet, but I want you to understand. If I have x to power r, this is variable, this is constant, this is called power function. Yes? If it is the other way around, r to the x, r is constant, and this one is variable, then it is called exponential, okay? Exponential. Today we are not talking about this, we are only talking about the power function. So be careful, that's a very important difference. So the formula that I put in this table is this one. If I have x to power r, the derivative r goes down, x to power r minus 1. Okay? And then, for example, let me give you some examples. So can you calculate the first one? So let me write it here on the board. You can see it on the slides. F of x is equal to what? 2x to the power of 3 minus 1 over 2x squared plus minus the square root of 3. Okay, can you help me because I want to make sure that you understand. If I will not have time to spend so much time. If you have troubles here, you can watch my videos in the high school. Okay, so what's f prime of x? Just tell me the answer.
6x minus 6x squared.
6x squared, 3 goes down, x to power 2. In principle, I should say that the derivative of this is the derivative of the first one minus the derivative of the second one minus the derivative of the third one. This is the way you have to think, but you don't need to write all the details. And extremely important to think in this way. And then the derivative of this one, it's a constant multiplied by a function. You pull the constant out and you differentiate this one. But the derivative of this one is 3x squared. So this is why you do it automatically and quickly. How many of you have troubles with this? Is that understandable? Yes?
Yes.
Okay. So then, what about the second one?
Minus x.
Minus x. What is the next one?
Minus 0.
Minus 0, which we don't write. So that's a
Yeah.
derivative. Yes? So what about this one, for example, the next one? F of x equals to 1 over x to the power of 3, the third root of x squared. If I want to differentiate this, how can I do that?
Make it compound.
Yeah.
So you see, the thing is that when you want to differentiate, this is not the case that all the formulas are in the table. You have to prepare it and then differentiate. Preparation part means to write it in a way that you can find it in the table or in your memory. Okay? So, do you think that this second row formula is enough for me to do this? Or I need more formulas?
It's enough.
It is enough if you know there are some formulas. Do you remember the nth root of a box to power n can be written as what?
The box.
The box to the power of a fraction, which this number goes to the denominator, this number goes up. Okay, so I can do that. So this becomes 1 over x to power 3 is just x to power 3. Instead of this one, what I can write? X to the power of 2/3. But then I have two powers with the same bases, different exponents. I write the same base, but I add the exponents. These are very elementary formulas. If I add this to this one, it becomes 11 over 3. But still, the preparation is not complete because this should be x to some power. This is 1 over x to some power. So how can I make it x to some power? Bring it up. And it becomes x to power minus 1 over 3. So if the differentiation is asked, this is not differentiation yet. This is preparation for differentiation. Now it is in my table. So now I can write what is the derivative? Minus 1 over 3 goes down. X to power. This one 1 unit less. Minus 11 over 3 minus 1 is minus 14 over 3. That's your derivative. Is it always differentiable?
No.
No. For example, is this function differentiable at 0?
No.
No, because 0 to a negative power means 1 over 0, which is not defined. So this is the preparation then. So all the formulas, all the ones that I have written in example 17 can be solved only using the second row. So no extra formula is needed, even the number 6. So for example, can you tell me what should I do for number 5?
Expand the bracket.
Yes, I expand the bracket, multiply, and then I use the same formula. But I also recommend you, what is the derivative of x?
1.
The derivative of x is 1. Why? Because x is x to power 1. So the derivative 1 goes down, x to power 1 minus 1, 1 x to power 0, it becomes 1. So the derivative of x is always 1. Especially a square root of x. I really want you to memorize the derivative of a square root of x. Otherwise, you have to do it like this all the time. But because it is ubiquitous, it is better to remember. It's 1 over 2 square root of x. The last one, you can also do it. Okay? This one, let me skip a little bit here. Yeah, this is... Usually it is not even given. The reason I wrote it here is because it is in your book. Yeah, I will come back to it at some point, probably tomorrow. So let me skip this one because I want to give you some other formulas. Okay, so now the derivative of sine and cosine functions. So the derivative of sine x is cosine x, but the derivative of cosine x is minus sine x. So you see, we add these two in our table. So sine x, its derivative is cosine x. Cosine x, the derivative is minus sine x. So it's extremely important that x is in radians. Yes, if I have time a little bit, I will talk about why this is correct. The proof of this is related to this theorem we learned before. Yes, so if you want to prove these formulas, this is related to this limit that we learned before. Okay. So can you, for example, tell me what is the answer to the next one, example 18? If f of x is this function, what is f prime of pi over 3? What should I do first? Can you tell me?
Find f prime of x.
Yes, it is extremely important. You have to find f prime of x first and then replace your x with pi over 3. Yes? So can you help me to write the answer here? So what is f prime of x? What is f prime of x? It is 3x squared and then 2 cosine x. So it becomes minus 2 sine x. And then I have 3 minus 3 cosine x.
What did you get?
Yes? And then the derivative of 2 pi squared is 0. Okay, so that's it. And then what I do, I replace x with pi over 3. And then of course you need to remember these things because you don't have any table in the exam, so you have to have this in your memory and put them and find the answers. Okay, we have 5 minutes yet. Let me also go to the product rule. So the product rule is among these general rules. Yes. So general formulas, I will add one more to it. What is that? If I have the product, it is not like sum or difference. It is not like that f prime g prime. That is wrong. You have to write f prime, but multiplied by the second one itself, plus the other way around. The first one itself, multiplied by the derivative of the second one. And that is one of the problems in the workshop that they are asking you. One time I have seen it in the exam as well. But the proof is completely written in your book. But it is good, try to find the way yourself, and then if you cannot, you can watch the problem. Of course, I have also proven this in all my videos for the high school students. Okay, so here, remember that the product, if you want to take the derivative of a product, don't say the derivative of the first one multiplied by the derivative of the second one. The derivative of the first one multiplied by the second one itself plus the other way around. Is that right? Okay. And for example, you see, if I ask you, if you didn't know about the product rule, can you still do something with the first one?
Yeah.
How? Expand. Yes? But there is no way you can do something for the second one here. So the second one, you have to use the product rule because it is really a product. And there is no way that I can get rid of the product. Okay, so that's why it is very important. So can you tell me how to do it? For example, if I want to take the derivative of this one, I realize it is a product. I have to apply the product rule. It means the derivative of the first one multiplied by the second one itself plus the first one itself multiplied by the derivative of the second one. Yes? And then you have the formulas before. The derivative of x is 1 times sine. X is copy and paste. The derivative of sine we just learned is cosine. So that is the this derivative. Okay. And then let me also talk about, we have a little bit of minutes, and about the quotient rule. This you also learned in high school. The quotient rule is another formula of this type. So if I want to put it in the right place, I have to put it here. There will be one extremely important formula that I will put here, and that is called the chain rule. We will talk about that tomorrow. So f over g prime, if I want to differentiate a fraction, The rule is the derivative of the numerator multiplied by the denominator itself. So let me write x here. Minus the other way around. And divided by the denominator to power 2. And that is called the quotient rule. And of course this rule works if g of x is not equal to 0. That's also good to see how you can prove this. You have to memorize all these formulas. Okay, so you have to have them in your memory. Just let me do one example and then I will start. I can do this tomorrow. So can we do this together? F of x is equal to what? Sine x divided by 1 minus 2 cosine x. I want to calculate f prime of x. So do you remember the formula now? So the formula tells you the derivative of the top one. So let us write it once. Multiplied by the denominator itself minus the numerator multiplied by the derivative of the denominator and everything divided by denominator squared. Yes? So this is the formula that I am using here. But you have to continue until there is no prime left. So this one, the derivative of sine is in table, is cosine. And I copy and paste this part. Minus, copy, paste sine. Okay, can you do this in your head? What's the answer?
2 sine squared.
2 sine. Yes, 2 sine. Because this is 0. Minus 2 is a constant. Derivative of cosine is minus sine. So it will get rid of this minus. But there is a minus sign here. No worries. So it becomes 2 sine. And then divided by this one to power 2. Okay, usually you have to simplify. So 1 more minute. So I multiply this in. So differentiation is finished here. Can I simplify a little bit more?
Yes.
How?
So
Between these two, you can factor a minus 2 out. What will be left? Cosine squared plus sine squared. But that's very famous. Cosine squared plus sine squared is 1. So the answer becomes cosine x minus 2 divided by 1 minus 2 cosine x to power 2. So that's the final answer to this problem. So I cannot cover everything now, but there's one more thing left from this lecture. So that's more or less good. Any questions? Okay, thank you.